we are very much looking forward to this.
Thank you very much for your presentation and for the opportunity of giving this talk here. I am a little off topic with the things that have been being discussed in the conference, but in the end, I think that we have a common goal, that is to look for systems where we can tune. So, as it was said, I work now in Zaragoza, but I'm only there for a sabbatical year. My permanent position is in Argentina, where I work for the National Atomic Energy Commission at the Laboratory of Neutron Beams. So I will present results on neutron diffraction experiments on ferroelectric polarization. So other interesting features of this crystal structure is that it is one of the very few compounds, oxides, where you can find the magnetic ion inside a purely tetrahedral environment. Usually you find octahedra, and you find a mixture of tetrahedra and octahedra, but a purely tetrahedral environment is difficult to find, and this compound presents that. And in addition to that, it presents, I will show you later, a geometry formed by triangular layers or kagome layers, which lead to a strong frustration of the very strong antiferromagnetic interactions between the covalents. So something very interesting happened when, instead of using a 3+ cation in this compound, a group in France 10 years ago tried to put calcium, which is a 2+ cation, instead in the place of the R site. And when they did that, contrary to the other compounds, a strong magnetic signal appeared below 60 Kelvin, and this is a ferrimagnetic order. And concomitant with that transition temperature, a strong signal in the dielectric constant measurements, indicating a very strong increase of the polarization. So this compound is not strictly you don't have a reversibility of the polarization signal, but what you have below 60 Kelvin is an increase in polarization, which is triggered by the magnetic transition, as you can see here, because as you apply the magnetic field, you can see how this change in polarization achieves a value at low temperature that is indeed very high for pure multiferroics. So the origin of this magnetoelectric coupling is supposed to be in a magneto-striction mechanism, and I will, well, I am signaling here the value of this jump. What I will be showing you today is what happens when you start playing with this 2+ cation at this site of the structure. So we replaced calcium by strontium, and we prepared a series of samples. We could achieve the highest level for pure samples was 7 atomic percent strontium, because if you go higher, you start to segregate strontium. So we did very careful measurements that we were putting strontium really at that site, and that the samples were pure. And the first characterization of the system was the magnetic measurements, and we immediately can see that the effect of adding strontium is quite impressive. There are a lot of things going on here when you start adding strontium. So the parent compound has this typical ferrimagnetic type of behavior, but already for a 2%, which is the orange curve, and 5 and 7%, you start decreasing. Here is a logarithmic scale in the magnetization. You start decreasing this magnetization, and also you start introducing these kind of behaviors with an hysteresis here and a plateau, which I highlight better in this figure. You can see that there is a region between 62 and 82 Kelvin approximately, where something else is going on, and the magnetization starts to get flat. And in that region where it gets flat, you have some features in the specific heat. So there's something going on there, and we wanted to see what was happening in this region. For this, we did neutron diffraction experiments. So in order to see the difference on what was going on in that temperature range, we needed to first be sure that the low temperature state was as expected, and what is as expected. This is a measurement for the pure sample with no strontium, and this is a measurement for the 2% strontium sample. And the refinement is done using the Rydberg method with the Fullprof program, and taking into account, of course, the magnetic contribution to the diffraction pattern. For this, we use the formalism of magnetic space groups. And the space group in this case is indicated here. And you see that we have a propagation vector for the magnetic structure, which is 0, 0, 0, which means that the magnetic cell is the same as the crystal cell. And the system is indeed ferrimagnetic, and it shows a net moment along the A-axis. If you do a plot of this structure, here you have the compound, and I've just removed all the atoms except cobalts, and I've put different colors for cobalts in a layer that is a triangular layer, and a pink layer that is a kagome layer. But you shouldn't think this as a layered structure, because actually they are coupled. And in the cell, there are 4 different cobalt sites crystallographically, different weak of positions, let's say. So this is a view from above. You can see here the triangular layer. These are cobalt 1. They are further apart. And then you have the kagome layer on top, if you look at from the z-axis. And you have the 3 remaining cobalts in the cell. And the magnetic structure is quite complex, but you can think of it as, I don't have enough contrast here, but you must believe me that here you have a zigzag chain running that way along the A-axis. And in this zigzag chain, they are coupled ferromagnetically. And then you've got the triangular cobalts and cobalt 4 that are also coupled ferromagnetically between them. So this gives a net moment only along the A-axis. So if you have a look at the strontium with 2% strontium doping, the diffractogram looks quite the same. And so we focused on this region, because here is where the magnetic signal is higher, and you can see if there's something going on in the magnetic order. So for this, we did thermodiffractogram experiments, which means that you vary temperature as you collect the diffraction patterns. And indeed, even for only 2 atomic percent strontium, we did observe that there was something going on between 62 and 82 that manifests with this peak and this other peak here, and some other small features. But indeed, the white arrows indicate the ferrimagnetic phase, and this is another phase that is different. So what was this second phase appearing there? We also measured the 5% and the 7%, and we observed that there were some common characteristics. We tried to fit that with the Rydberg refinement. And when you try to do that, the first thing you look for is a propagation vector to see how the magnetic structure correlates with the crystal structure. And in this case, we found an incommensurate phase, which means that you have a modulation with a very long modulation period. This is 510 angstroms along the z-axis, and antiferromagnetic along A and B. This is the propagation vector that we find, and we could fit the 3 samples data with this model. But which is the model? You have to find or to propose a model for this magnetic structure, not just the propagation vector. To do that, using neutron diffraction, one strategy is, when you are dealing with incommensurate magnetic structures, which are the hardest to deal with, we use the superspace group formalism, which is very recently implemented in Fullprof from 2020. And you think of the magnetic structure as a basic structure with a conventional magnetic group, a Shubnikov group, and you add a modulation function with a propagation vector k, which is the one what we found from the data. When you write the magnetic moments at each crystallographic site in this way, then you can inject this into the Fullprof program and make a refinement of the directions and the moduli of the magnetic moments at each site. And when we did that, we obtained a model, a magnetic superspace group, which is this one. And let me show you. This is the modulation of the magnetic moments at each site, and you will see that in the triangular sides, you have not only a modulation of the strength of the magnetic moments, but also a rotation, an helical rotation of the moments. And at the kagome sides, you only have a modulation of the amplitude of these magnetic moments. So this is quite a complex structure, but it is not so surprising because of the strong frustration that this lattice presents. This is the first time that this plateau in the magnetization is explained in terms of a magnetic model. It had been observed in other systems where the substitution site was not calcium, but cobalt, for instance, by replacing cobalt with zinc, by replacing cobalt with aluminum or other cations. They also observed a plateau in the magnetization, but there wasn't a model proposed for this phase. So this is the first big result that we got from these substituted compounds. Sorry, the other way. And as I mentioned, you have different modulations depending on which layer of the structure you are looking. But next, we had a look at what happened below that phase, below 62 Kelvin approximately. So first of all, if we have a look at the lowest doping level, you need to obtain at the lowest temperature the ferrimagnetic structure that I showed you in the beginning. But what happens in the middle between this incommensurate phase and this ferrimagnetic phase? And in the middle, what we observe is that the incommensurate phase locks to a commensurate propagation vector. Okay, great. This propagation vector is now 1/2, 1/2, 0. So you lose this modulation along the z-axis. And the difference between both models, if you compare them, it is quite difficult because they are complex structures. But the main difference is that the ferromagnetic coupling that we observed at low temperatures between these two cobalts now turns antiferromagnetic. So all in all, this structure does not have any net magnetic components, but you need to remember that the Newton diffraction experiments are done at zero field. You don't have any applied field. As soon as you apply some magnetic field, this can change completely. So this is something to have in mind. Another thing that we observed, and is indicated with these black arrows, is very tiny additional peaks. These peaks are of a magnetic origin, and they are not accounted for by any of the models that I have been discussing, nor the ferrimagnetic one, nor the ferrimagnetic one, nor the commensurate antiferromagnetic one. And so we call this a second additional incommensurate phase, because if you try to index the position of these peaks, they are compatible with a propagation vector that is also incommensurate. When we increase I'm just finishing here, when you increase strontium content to 5 and 7, what you get is that you keep this commensurate 1/2, 1/2, 0 phase all the way down to Kelvin, 1.5 Kelvin, and you also keep these additional small peaks that we can't find a model. We can't find a model for these peaks because they are very tiny, and we are immersed in a very complex phase already, so it is not reasonable to obtain a complete model for these peaks. But they are there indeed, and they are there in the 3 samples, so something is definitely going on. And we think that this is strongly related to what happens when you increase magnetic field. In the magnetization, the increase of the magnetic field applied has a strong effect also in these hysteresis and the coexistence of these phases that we are observing. So the other way. So to sum up, as I told you, it had been repeatedly reported in the literature, the effects of doping and the destabilization of this ferrimagnetic phase by substituting mostly the cobalt side, but not other sides in the structure. So we present results for the substitution at calcium side. The strontium addition really favors complex antiferromagnetic arrangements. We proposed a model for this incommensurate phase. And we also propose a scenario at low temperatures where there are two phases in coexistence, two competing phases. One is one-half, zero phase, but we also observe additional peaks that can't be accounted for by these models. And this highlights a very complex energy landscape and the possible role that magnetic field could have on this balance of phases. And thank you for your attention.
So these are very frustrated layers. You said also that interlayer coupling is relevant. So for the kagome, I wouldn't even know what kind of order I would expect, but for the triangular, I would expect this 120 degrees ordering. But that would be one-third, one-third, zero,
yes.
right?
Yes, and that doesn't...
Do you have any understanding why you get another ordering wave vector?
No, the first guess, of course, was to look for the one-third, one-third, zero, because this is expected for this kind of triangular layers arrangements, but that didn't fit the data at all. So we said, okay, we have to expand our search for the propagation vector. So I think that the interaction between the layers is playing a significant role, because if they were isolated, you would have that order for sure.
Thanks.
So, yes, so I have like maybe you mentioned this and I missed it, but you started discussing this material from the context of the magnetic phase, which you extensively described, and then you also mentioned that there is like a polar phase.
The structure, the crystal structure, yes, is a polar.
Yes. Yes. So it's in a polar group. That's
yeah.
While all of this is happening, and is there any reason why, like, or is the connection between these two things are completely decoupled? You're only thinking about the magnetic part, and
I am studying the magnetic part because I'm using neutrons, but the possible origin for this coupling of the increase in polarization that you observe if you measure the electric constant, or if you make experiments of polarization. This is probably the origin of that is magnetostriction, because I didn't show it, but the ferrimagnetic phase has a very sharp change in the lattice constants, a stepwise change in the lattice constant. And this step disappears when you start doping. So that really sharp magnetostriction phenomena is driving probably the increase in the polarization, which is always there because of the polar nature of the crystal space.
But beyond that, there is no like a strong effect on what kind of magnetic structure you expect, or how it would evolve?
Not that we have found, and as soon as these other phases start to emerge, the polarization is not so, the increase is not so big, so it doesn't go in the direction that we would like for, let's say, for applications, but I think it contributes to our understanding of the stability of the system.
So these cobalt sites, are they a steady line of charge approximation, or do you have different moments on the cobalt plate that no one, or did I miss that?
You have slightly different models. I think I went very quickly over that. But the charge order was proposed in the first publication of this structure, but it was based only on a difference of interatomic distances. and it was not very robust. Some years later, people conducted more precise synchrotron radiation measurements, and they showed that you really can't justify a charge ordering scenario. So I think we're here. You can see that there is a difference between the strength, the magnetic moments, but you can't really say that it's charge order. Okay, thank you. Yes, sure. Thank you very much.